All right, today we'll talk about the environmental consequences of energy use, okay? Which is what this course is about. You learned that today the world is getting 80% of its energy from fossil fuel sources, and our goal is to move toward renewable energy sources, okay? All the detrimental environmental consequences, that is the bad results of our energy use are because of fossil fuel sources. Okay, essentially all our environmental problems are because of fossil fuel use. Okay, so we'll look at some of that. Okay, so here are the numbers. So this is, you've seen this graph before. This is the predictions of Stanford University group. Okay, so what we are saying is, okay, this in 2012, what this number is saying is 12 terawatts, that is 12,000 gigawatts. A gigawatt is roughly a Hoover Dam, you can think of that. So in 2012, to run the world, you needed 12,000 Hoover Dams running 24/7. And most of our energy was coming from fossil fuel sources. Okay? If you keep the same mix, if you keep using fossil fuels essentially, in 2050, which is 25 years from now, within your lifetime, you would need 20,000 Hoover Dams to run the world. That's what that graph is telling you. But if renewables energy sources come into play, which will happen, again, within your lifetime, in 2050, all you'll need is 12,000 Hoover Dams. Okay?
2050?
Yeah, 2050. So why do we need fewer Hoover Dams by 2050? Okay, if you run the world on wind and solar, that's on electricity, you're more efficient. If you drive a Tesla is 90% efficient. What does that mean? 90% efficient. Anybody? Yeah?
90% of the electricity that's going into pushing the car.
That's right. So, very good, my friend. So what our friend just said is 90% of the energy stored in the battery is converted to motion. Okay. Whereas if you run a gasoline car, what is the efficiency of your gasoline car? 20%. So 20% of the energy stored in the gasoline is converted to motion. What happened to the other 80%? I'm sorry? Yeah, you threw it out the window. Okay. All right, so this is what, okay, so, I mean, the benefits are immense. Okay. Now, many of the world's greatest environmental challenges are because of burning fossil fuels. Okay. So when we switch to renewable, air quality, everything will be good. Okay, a lot of our environmental problems will go away. Yeah. So now I'll point out a couple of numbers. Pollution from fossil fuels, burning fossil fuels prematurely kills 5 million people annually. Okay. Well, if somebody told me that you're going to cut my lifespan from 75 to 65, I'm not going to be terribly happy about that, right? Okay, so that's the kind of stuff, that's what we're talking about here. And here's an amazing number. So this is the same group. Okay. So Stanford University group estimates that globally, by the way, do you guys know what is the annual GDP of the Earth today? It's about $100 trillion. Okay? So group estimates that globally 22.8 trillion in health costs can be saved if complete switch to renewables by 2050 is implemented. So if we keep on this track and by 2050 we are completely running on renewables, The health savings would be $22.8 trillion. The health cost savings will amount to 12.6 per kilowatt hour. Does this number mean anything to you guys? This is what you pay for your electric bill today. A kilowatt hour is a unit of energy by which the electric bill company bills you, and that's what you pay by. Okay, so what this is saying is, if you switch to renewables, which is going to happen, okay, the health cost, the money that you're spending less than healthcare will pay for your electric bill. Your electricity will be free. Okay, so I don't know, let's say you're paying $200 right now, a month or whatever, okay? I pay about $125, okay? So as the world is switching to renewables, okay, my health savings, I'm not getting as much as sicker because we're switching to renewables, and that saving is paying for my electricity bill. Yep.
How is it, this is probably a dumb question, how is it, killing people, like what diseases, like I'm sure it affects the lungs obviously, but like what diseases are we getting that it's killing that many people?
It's mostly respiratory diseases. Okay. And acid rain and stuff like that. Okay. All right. So anyway, switching to renewables is we have no option. It's a good thing, and so the question is, the faster we get there, the better it is for us. Okay. And why are we using fossil fuels again? It's cheap. Okay. And it's who's dying? Poor people are dying. So, and they have the least. Well, anyway. All right. So here are the various problems: thermal pollution, chemical pollution, particulates, and greenhouse gases. This is the biggest problem. Okay, what is this thermal pollution? Let me give you the big numbers. Do you guys remember how many Hoover dams does it take to run the world currently? I'm sorry? 18,000. Okay, very good. 18,000 gigawatts. Okay, that's how much. And currently, let's say we are using 100% fossil fuels. Okay, so what this number means is 100. You're using 18,000 Hoover dams worth of Hoover dam, and all of that is burning fossil fuels. How efficient are fossil fuel plants? How efficient are coal power plants?
40%.
Yep, 40%. Very good, my friend. Okay, so that we'll say 33%, just so, because I'm not good at math. Okay, that means 6,000 worth of Hoover dams is really being used, and 12,000 worth of Hoover dams, you have to throw away this heat. So to run the world, this is what you're using, and this is what you have to throw into the environment. That is the thermal pollution. Okay, you have to constantly dump heat into the environment, and a lot of it. Okay, so for $1 of energy you're using, you're dumping $2 worth of heat into the environment. And this won't be a problem when you switch to renewables. Okay. Where are you dumping this heat? If you dump this heat in this room, the air would get too hot. Well, actually, it ends up being that you dump the heat into large bodies of water. Okay, why do you dump the heat in large bodies of water?
Cools it down.
Okay, water has a high specific heat, so for a given amount of heat you add to the water, its temperature doesn't rise as much. Okay. So if you dump the heat into land and you dump the same amount of heat into water, In land, the temperature would rise 5 times as much. Okay, so water can absorb a lot of heat. So that's where you dump, and also you dump. Nowadays, a lot of thermal plants will dump the heat into the atmosphere. Okay, so we'll talk about that. So getting rid of you have to get rid of a lot of heat. So we'll talk about thermal pollution. Chemical pollution, particulates is small particles, and if these particles get in your inner in the lower lungs, the small particles can get in the lower lungs, then that'll cause a lot of health problems. Okay? And the greenhouse gases, of course, it's causing global warming. What is the current temperature today? You guys remember?
14 point something.
And 14 degrees Celsius was in the 1850s. What is the temperature today?
15.2.
Very good, 15.2 degrees Celsius. Okay? And what is our goal?
To stay under 15.5.
To stay under. Okay, so that's very optimistic. I hope it happens for you guys, but not likely. So we would like to stay below 16. Okay. So that's the problem we'll talk about. Okay. So again, fossil fuels are the culprits for most of our environmental problem. Okay. Internal combustion engines and coal and gas-fired generating stations. Okay, so there's the fossil fuel use are the major contributors to all categories listed. Okay, all these categories. So today we'll talk about all these categories one at a time. Okay. All right, thermal pollution. You have to get rid of 12,000 gigawatts of heat. Okay, that's 12,000 gigawatts. What does that number mean? 12,000 giga is billion joules per second. That's how much heat every second you got to get rid of. You got to dump. Okay. All right, so here are the big numbers. I mean, this is the numbers for the US in 2021, and you can just multiply it 4 times to get the global numbers. Okay. You can add this up: natural gas, coal, and petroleum. That adds up to about 80%. Okay. Okay, so to run the US annually, you need 100 quads of energy. This is the primary source. Okay. Because our energy is coming from fossil fuels, 2/3 of it that has to be dumped. Okay, it's unusable. Okay, let me say this again. This is 100 quads. So let's say this is it's roughly about $1 trillion. 700 billion of that has to be thrown away out the window. 300 billion is useful. Okay? If all of that was electricity, which will happen when? 2050. Why will all that be electricity?
It'll be cheaper.
No, because it's being generated by wind and solar. Okay? Then 90% of it will be used. You won't be throwing anything out the window. How fast do you want 2050 to be here? Right? Okay. So with primary energy mix of 80% and 20% fossil fuels and 20%, almost 65% of the primary energy is lost in the conversion process. Okay. Because Mr. Carnot puts a limit on the efficiency of heat engines. Okay. You guys are following this thing? Okay. All right. All right. So again, so we'll talk about the first thing: thermal pollution. Okay. So a thermal power plant. Why? What happened? Okay. A thermal power plant. I wonder if the door closing shook the wall a little and we lost connection. So a thermal power plant A thermal power plant is any plant where you first generate heat and then use that heat to produce electricity. Okay, so coal, natural gas, and nuclear power plants are thermal power plants. To produce 1 gigawatt of electricity, that's a Hoover Dam, you have to get rid of 2 gigawatts of heat. Okay, so even in a nuclear power plant, that's to produce $1 of electricity, you have to get rid $2 of heat has to be thrown away. And here's a cooling tower. What this is doing is this is dumping the heat into the atmosphere. Okay, so there are two sinks, places where you're dumping heat. You're dumping heat either in the atmosphere or in bodies of water. Okay, so those are the two places you're dumping heat. So you'll see that a lot of nuclear power plants and all thermal power plants, a lot of times they're built near large bodies of water. Okay, that's why. Okay. So an automobile engine, the efficiency is 20%. For a thermal power plant, it's 35 to 40%. Okay. So again, $1 is used, $2 has to be dumped. Okay, so let's see where you dump it. Okay. So thermal generating stations that burn coal, oil, or natural gas need to release unusable heat into the environment. Now, you might come across this word called cogeneration. Now, in some instances, let's say you build a plant near New York City or something like that. In the winter, New York City needs heating. Okay. So you could send the heat to heating in the buildings. Okay. So for instance, in New York City, 100,000 buildings are heated that way. Okay. But you can't build a thermal power plant everywhere near the cities and stuff like that. So in case you can use that heat, sometimes it's used. Okay. But most of the time you're dumping it. So either a large body of water or the atmosphere is used as a heat sink, a place where you dump the heat. And what is your concern? What is it that you want to ensure? That the temperature where you're dumping the heat doesn't rise too much. Okay. So for instance, France gets 75% of its electricity from nuclear power plants. Okay. And during the summers, so you're dumping heat in the rivers, and in the summers, the rivers were running low, and you dump heat in the rivers, you need more electricity in the summers. And the water temperature rose, and the fish started complaining. Okay, so that was a problem. You guys following this? Yeah. Remember, if we're doing this just because there's a good chance you'll become president, and you'd better make good decisions, right? All right. So we'll first talk about dumping the heat in bodies of water. Okay. So here's a thermal power plant. You're taking in cold water. The heat is dumped into the cold water, and then you're putting the warm water back down there. Okay. So now, what are the problems with the warm water? Okay. Well, why did you use water in the first place? Water has a high heat capacity. What does that mean? For a given amount of heat dumped, the temperature doesn't rise as much. Higher the heat capacity, lower the rise in temperature. Okay? And can absorb a considerable amount of heat without its temperature rising too high. In addition, water has a high thermal conductivity, and heat transfer is efficient. What that means is, if you dump heat here, the heat will flow out into the rest of the body of the water fast. Okay, that's a good thing. Yep, go ahead.
Does that like mess with like the ecosystems and stuff?
It does. Yeah. So okay, so that's what we're going to talk about. Appropriate bodies of water are fairly common, and in addition, cooling infrastructure is simple and economical. Okay. Yeah, so what drives most of industry's decisions? the bottom line and the cheapest technological solution. Okay? Yeah. All right, so here are the problems. Decrease in oxygen content. Okay, so warmer waters hold less oxygen, okay, and that's bad for life. Changes in temperature of the body can affect reaction rates. Okay. So I'll just tell you one little thing about that. Okay, so let's say we're cooking potatoes. You don't like potatoes? All right, so let's say we're cooking potatoes. What temperature does water boil at? 100 degrees Celsius, okay? And these potatoes cook in 1 hour, okay? Now here's if you could get the water to boil at 110 degrees Celsius, now for every 10-degree rise in temperature, the reaction rates double, so potatoes would cook in 30 minutes. Now, if you could cook the potatoes in 120 minutes, 120 degrees Celsius, how fast would they cook? 15 minutes. Let's see if that thing goes off again. Well, how do you get the water to boil at 120 degrees Celsius? Okay, so water will boil at 100 degrees Celsius at 1 atmosphere. If you could get water to boil at 2 atmosphere, it would boil at 120 degrees Celsius. And that's what a pressure cooker is. Okay, so you build the pressure to 2 atmospheres. Do you use that pressure cooker? No. I'm sorry?
I said I have before.
Yeah. So it cooks in 2 atmosphere. You're saving energy, okay? Anyway, so the point is, why are we talking about this? Okay, so, I mean, your body, you really are a factory of millions of chemical reactions happening at various rates, and they're interdependent. Okay, so for biology, if you raise the temperature, now you're changing the reaction rates of very complex organisms, and stuff might go awry. Okay, so they affect reaction rates. That's what we're saying. Changes in thermal profile can affect the natural seasonal mixing of water in the lake and stuff like that. Okay. So nutrient cycles and all that, it'll affect that. All right, so that's dumping heat in the water. Now we'll talk about dumping heat in the atmosphere. Again, how much heat are we dumping globally? Remember, 12,000 gigawatts, okay, currently. So transfer of heat to the atmosphere through cooling towers. These are cooling towers. This can cause increase in fog and precipitation in local areas. But, you got to pick your poison, okay? So we've talked about the first guy, thermal pollution, okay? You know the magnitude of the problem, and you know where we are dumping the heat. We are dumping heat in the atmosphere and water, okay? Now we'll talk about chemical pollution. Question?
I'm just thinking because like the cooling tower is like steam
Mhm.
coming out. I was like, I never saw the heat just going directly in the ocean. That in that example you have like 2 pipes underwater, and it's taking in like the
Mhm.
cool water and
Mhm.
pushing out, and it's coming out as hot water
Mhm.
instead of steam. I was just thinking, I wonder if that's worse than steam in the atmosphere, like hot water. I don't know.
No,
How
it's.
hot does it make the water?
So in France, when the problem happened, the temperature had risen by about 10 degrees Celsius, I believe. Mhm. Okay, so by the way, I wanted to. I love this thing. All right, so here's what we'll look at the details of this diagram. Here's coal, you are burning coal, and what do you do with the heat released? You're boiling water and steam. Okay, so here's cold water coming in, you absorb the heat and you're producing steam. What does the steam do? It goes to a turbine and the steam hits the blades and it turns the turbine. And what does the turbine do? Your goal is to produce electricity. The turbine is turning this piece of wire between magnets. Okay, and that's how you're producing electricity. Okay, and then then you get rid of the steam. I mean the steam. You have to condense the steam, and that's where you have to dump the heat. So here's a cooling tower where you're dumping the heat into the atmosphere. Okay. And again, in the steam, only about 1/3 of the heat content of the steam got converted to this motion of the turbine, and 2/3 of the heat content of the steam had to be dumped out. Okay. So that's what was happening. Okay. So chemical pollution. Okay. So again, burning fossil fuels. So these are some of the problem pollutants. Carbon monoxide. We'll talk about that. And carbon monoxide. Nitrogen compounds and sulfur compounds, sulfur oxide compounds. These lead to acid rain. And then hydrocarbons. You've seen that black smoke that comes out of vehicles sometimes, and that kind of stuff. Okay, so those are hydrocarbons, incomplete burning of hydrocarbons. Okay, so this tells you the CO2 released from mostly vehicles. Okay, and let me come to that. Let's talk about that first. Okay, so carbon monoxide. Here's carbon monoxide. Okay, so carbon monoxide. This has immediate health effects. Okay, this is carbon dioxide, which causes global warming. Okay, so carbon monoxide happens when you're burning carbon, coal, and carbon contained in hydrocarbons. If you have insufficient oxygen, you produce carbon monoxide. Okay, see, 2 carbon atoms, 2 oxygen atoms produce that. Now, if you had enough carbon, if you had enough oxygen, then you would produce carbon dioxide. Okay, and so the detrimental effects of this guy are within a short period now. Okay, within the next few hours. The detrimental effects of this guy are over hundreds of years. Okay, so you can die now or you can die later. All right. So again, carbon monoxide is produced by insufficient oxygen when you're burning stuff. Okay? Did you guys understand that? All right. What does carbon monoxide do? So here's the problem. Carbon monoxide is 200 times as reactive with hemoglobin as oxygen. Okay. What is the job of your lungs? I mean, your blood comes, red blood comes there. Your hemoglobin absorbs oxygen and takes it to the body. Okay. Now, if there was carbon monoxide in the air, the carbon monoxide would bind to the hemoglobin, and now you can't absorb oxygen anymore. Okay. So, exposure of CO2 for an hour, if you were exposed to carbon monoxide for an hour, 100 ppm. What is 100 ppm? 100 parts per million. Okay, so for every million atoms, if 100 atoms were a carbon monoxide and you were exposed to that air for 1 hour, you would have headaches and confusion. 300 parts per million unconsciousness and 600 parts per million death. Okay. So carbon monoxide produced by vehicles dissipates in a in time scales of hours. So you produce carbon monoxide, and that is in the air for several hours. Okay. So this graph, what this shows you is, okay, 6 a.m. So this is carbon monoxide is produced by vehicles. Okay, and you're going to the office, carbon monoxide levels increase, and coming back home, carbon monoxide levels increased in the atmosphere. Okay. Over time, we placed laws to prevent that, catalytic converters, okay, and so the levels have gone down. All right, so here are the numbers. Even a properly tuned gasoline engine will produce more than 30,000 parts per million of carbon monoxide in the exhaust stream. More than 30,000 parts per million. 600 parts per million can cause death. Okay? So you don't want a closed garage and get your car running.
Do all those side effects happen like quickly or like?
Pretty quick.
Yeah.
In a poison area.
All right, so an exhaust leak can allow CO2 escape before it's converted to non-toxic carbon dioxide in the catalytic converter. So that's what a catalytic converter does. Okay, it'll make sure that the carbon monoxide reacts with whatever little oxygen there is. And becomes CO2. Okay. Exhaust systems must be gas tight from the engine to the end of the tailpipe. Okay. Catalytic converters, they were expensive. That's why the auto companies were not willing to put them in, but now you can't live without them. Okay. Found in cars and trucks combine oxygen with carbon monoxide to produce carbon dioxide. Okay. So high concentration levels in the exhaust manifolds, typically from 300, these guys reduce from 300 parts per million to 1,000 parts per million coming out of the tailpipe. Okay. So that is still harmful. So you don't want to, even with a catalytic converter, you don't want to run your car inside a closed garage. Okay. So these are effects of emission controls that the EPA put in place. Okay. So this is grams per kilometer run. Okay, so if you were driving in the 60s, which most of you guys weren't, but the grams of CO emitted per kilometer driven was that, and now you see it's less than 2% of that. Okay, so these are the effects of emission control. Any questions? All right, what percentage of air is nitrogen? 78% is nitrogen, 21% is oxygen, and the rest is less than 1%. Okay. Now it turns out if you burn anything at a high temperature, over 1100 degrees Celsius, and this can potentially happen in thermal power plants, you will combine nitrogen in the air with oxygen and produce nitrogen oxide compounds. Okay, so burn anything at high temperature and you are going to produce nitrogen oxide compounds. Okay, so this is nitric oxide, and this can combine with ozone to form nitrous oxide, nitrogen dioxide. Okay, and this is harmful. Okay, so it causes respiratory irritation and heart damage depending on the concentration and exposure. And this will also combine with moisture in the atmosphere to produce nitric acid. Okay, so look at this. This is in Beijing, and they had to clean this up before the Olympics in 2008. They closed down all the thermal power plants near Beijing. Okay, so the thermal power plants were causing this. Okay. So in the middle of the day, you need a lot of electricity. Okay? And so the thermal power plants are running in the middle of the day, and nitrogen dioxide levels go up. Okay? That's what it's showing. So this is showing you daily fluctuations in Beijing in 2008. Okay. Okay. So we've talked about thermal pollution, chemical pollution. Okay, now we'll talk about the other guys. So the hydrocarbons, if the combustion of the fossil fuels is incomplete, the unburned hydrocarbons can be released to the atmosphere. And again, vehicles cause the most. Again, industries cause less, because for them, if it's an incomplete burn, that's money going out the window. Okay, and they'll make sure that that doesn't happen. So health effects range from eye irritation to lung disease and so on. Okay. So they've been greatly reduced by emission control standards on vehicles. Okay. Sulfur dioxide, this causes acid rain. Okay. This happens when you burn coal in thermal power plants, and if you guys refer to your notes from the previous chapter, if coal formed in freshwater swamps, it has less sulfur, but in brackish water, it has more sulfur. But anyway, I guess so whenever you burn coal, okay, it produces sulfur dioxide, and coal is the main culprit. Okay. All right, so a thermal power plant burning coal containing sulfur dumps sulfur dioxide in the atmosphere. The sulfur dioxide combines with oxygen to form sulfur trioxide, and the sulfur trioxide combines with water to give you sulfuric acid, and that's acid rain. Okay. So neutral water has a pH of 7. Acids have lower pH. Okay. So acid rain has pH levels ranging from 4 to 5. Okay. The more acidic the rain is, the lower its pH is, and the more harmful it is. Okay. You don't want acid raining down on you. Okay. So you guys understand how acid rain comes about? Yeah. All right. Well, what does acid do? Okay. Acid rain do? Okay.
Erodes.
I'm sorry?
Erodes things?
I'm sorry?
Acid erodes things?
Yeah, it erodes things, but more than that. Okay, so acid rain leaches aluminum from the soil. Okay, so aluminum is bound to compounds in the soil, and when acid rain falls, it frees up the aluminum. The aluminum is absorbed by trees, and that's harmful to them. Acid rain leaches aluminum from the soil. The aluminum is harmful to plants as well, animals. Yep.
So then why are they allowing the patents for chemtrails that has aluminum and uranium to display it in our atmosphere? If they know it's doing that.
Patents for what?
The United States has government patents for chemtrails, not the contrails, nothing like that. It's chemtrails, but they're seeding the atmosphere. So if they know this is causing things, why are they putting aluminum in the atmosphere to go, it just doesn't make sense.
What are the chemtrails? I don't know.
Chemtrails,
Yeah. And what is the problem
that they're spraying in the atmosphere.
to do what?
Who knows?
No, I mean there was
No, it's weather control, I don't know, I mean, if you look up the patents,
Okay.
It's out of my scope.
Yeah,
All
yeah.
I'm saying is I know that they're doing it, and they have the patents,
Mhm.
so if they know that it's doing this, and, for all these years, because I'm 48, right, so I try not to do a lot of plastics, I don't do a lot of, conserve everything,
Mhm.
but the people that are supposed to be taking care of us aren't doing it. Or not taking care of us, looking out for us.
Well, it's all cost-benefit analysis. If the cost is bearable for the benefit obtain, they'll do it.
Well, obviously, they have an unlimited write-up of cost, you know what I'm saying? So to them, it just doesn't make sense. Like, we care so much about our earth, but the ones that be are
Not enough.
spraying aluminum in our atmosphere.
Anyway, so I don't know the problem. I don't know what the problem is being solved. And again,
It
but
just doesn't make sense.
yeah, it's mostly cost benefit analysis. That's what's done. Okay. Acid rain also removes minerals and nutrients from the soil, and that trees need to grow. Okay, so calcium and magnesium are leached from the soil. Leached meaning these are in compounds, and that they are okay. So they are leached into the soil. Okay. At high elevations, acidic fog. So if you're in high elevation and you have acid fog, that'll damage leaves. Okay. Might strip nutrients from leaf foliage. Okay, so aluminum, calcium leach from needles and membranes. Okay, decreased cold tolerance, increasing freeze injury. So, for a while there, you could see in the Appalachian mountain range all these trees damaged from acid rain. You Google some of these pictures. Okay, so acid rain causes paint to peel, corrode steel structures such as bridge and stuff like that. So you're decreasing the lifespan of bridges and stuff. Okay. All right. So again, this nitrogen oxide compounds are whenever you burn stuff at high temperatures. Sulfur dioxide compounds come from burning coal. Sulfur containing coal, okay, and both these compounds produce acid rains, okay? Lead to acid rain. Okay, and now we'll talk about particulate pollution. Okay, so I mean these are dust particles mainly produced during combustion of coal in power plants. Also occur from domestic use of wood, agriculture, automobiles, forest fires, and chemical pollutants. Okay, so now it's the size of the particulate that matters. Okay, so roughly, so they are categorized into two kinds: particulate matter of 10 microns, consisting of 10 micrometers or smaller, and 2.5 containing particles of 2.5 micrometers or smaller. A micrometer is roughly the size of a cell. Okay. These guys or smaller can be inhaled into the lower respiratory system, causing serious health issues. Okay. So if they get into your lower respiratory system, they can cause serious issues. So this is a world map showing you particulate matters of 2.5 micrometers of less. Okay, so this is in grams. Okay, this is probably because of the desert and so on. Okay. So in a lot of the South countries, the rich countries don't have as much of a problem. Okay. All right. So here's how you, so removal of particulate pollution. So in a thermal power plant, so let's say a coal power plant, okay, you have smoke that's coming out that has particulate pollution. Okay, so you want to remove that particulate pollution, and I was trying to look for a picture there. So what removes it is something called an electrostatic precipitator. So what happens is the following. So here's dirty smoke coming in. Okay, so and this has the particulate matters. Okay, so what this is these are metal plates, and these are metal wires going in between. And what you do is you probably apply 25,000 to 100,000 volts between them. And then what happens is these wires spit out electrons, and these electrons will stick to the particulate matter. The particulate matter becomes negatively charged, and the negatively charged particulate matter goes and sticks to the positive plates. Okay, and you can remove 99% of the particulate matter this way. Okay, did you guys understand that?
So why don't they put those on all vehicles in the front?
Well, getting this kind of voltage is hard. Okay, so you can do this for thermal power plants.
On a smaller scale?
Well, you need high
I'm just saying
voltage.
if there's always a positive, negative, you know what I mean? Like
Mhm.
if there's something negative, there's gonna be a positive to fix it.
Yep. Yes, so, and generally, if they aren't fixing it, that's because of cost issues. Okay. So even these guys, the big boys, so these guys were reluctant to put these electrostatic precipitators in place. And for the longest time, they got away with it because, okay, so they're dumping these particulates in the atmosphere. You're affecting the people living close by, and who was living close by? Poor people. Okay. And so you could get away with it. Okay. How much does this cost? 2 to 4% of the plant's electrical energy output goes into operating these things. Okay. So for every $100, $2 has to be spent on this thing. Okay. And that's why they were reluctant to do it. Mhm.
So those are essentially like big magnets? Is that what?
Yeah, you can think of it that way. So again, so you're burning coal, and the exhaust gases contain small particles, and you are trying to get rid of these small particles. Okay, so you pass it through this thing called an electrostatic precipitator. It could be as big as this room. Okay. It contains these metal plates and wires. You apply 100,000 volts between them. And when you apply a high voltage, these metal wires will spit out electrons. Those electrons will stick to these particles, and now the particles have become negatively charged. What do negative charges do? They go and stick to positive charge plates. Okay? So all these guys go and stick to these positive charge plates. You remove the particle, and now you can dump the smoke out. Every once in a while, you have to shake these plates and get all the particle matter, sweep up the particle matters. Okay. Mm-hmm. What happened by doing this? Now all these people living around your thermal power plant, they're living healthy lives. They're happy. Okay. All right. You guys understanding this? Okay. So now I'll need your attention here. This is the most complex thing we'll talk about. Okay. And this is important. Okay. So here's one of I love this statement. The solution to pollution is dilution. Have you guys heard of this? All right. So the solution to pollution is dilution. All right. So let's say, you burn something or something like that. You created pollution. Okay. Now this is warm generally, so a warm packet of air containing pollution. Now, if the air is colder around it, what will happen to the warm air? What happens is the warm air is less dense than the cold air, and it'll rise up. Okay? How long will it rise up? Till it gets to a point where the temperatures of the surrounding air is the same. Okay? If the surrounding air is cooler, it will keep rising. Yeah. And if it keeps rising, if it rises high enough up, then it becomes somebody else's problem. So that's what you want, right? It gets high up, it gets caught up in winds, and then it'll get dispersed into the atmosphere. All right. So did you guys understand that? So let's say you have a packet of warm air with pollution. What is it that you want? You want it to rise up and then get dispersed. If it stays trapped, you're breathing the pollution, the bad air. And you don't want that. You guys understand? All right. So now we'll get to the graph. All right, so you want this pollution to rise up and get dispersed. Okay, so if you take a packet of air and it rises up, okay, as it rises up, it cools down as well, because here's the reason why it cools down. A rising packet of air, the pressure is lower at higher elevations, it expands and it cools down. Okay, so this is how a rising packet of air would cool down. So this is altitude. Okay, so if it starts off at ground level at 20 degrees Celsius, what this is saying is if it rises up 4 kilometers, it will have cooled down to minus 40 degrees Celsius. Okay. Yeah. So now, if the air temperature, the atmosphere temperature is like this, okay, no matter what height it got to, it's warmer than so it got to this height, the surrounding air is cooler. You guys understand? If the atmosphere's temperature is that profile, this warming air will keep rising, and so this is unstable atmospheric condition, meaning a warm packet of air will keep rising, which is a good thing. Okay. Did you guys understand that? Whereas if the atmospheric conditions were like this, a warm packet of air is, if it's rising, it's colder at any height, it's colder than the surrounding air, so it won't rise. And it'll just stay trapped. Okay, so this is the temperature profile you want, so that a warm air packet of air keep rising and the pollutant will get dispersed. If it's anything like this, or you can have this is called temperature inversion. Temperature inversion is the temperature is rising with height. Okay, and if this happens, that's bad news. And then that can happen in cities. Okay. All right, so here's what I want you to remember about this thing. What you want is, even though the word is unstable, it's sort of a negative connotation. What you want is an unstable condition for the atmosphere, meaning a warm packet of air rising should keep rising. Okay. So thermal inversion, this condition occurs during evenings. The Earth's surface, the land is cool, the Earth's surface no longer radiates as much heat, enabling and not warming the air close to the ground. Okay, so this can arise in the evenings. Okay, a temperature inversion in London in 1952 lasted 5 days from December 5th to 9th. Okay, and back then we didn't have emission controls as much, so and because of industries, there was a lot of polluted air at low level. The result was the worst pollution-based fog in the city's history, and over 12,000 deaths above normal occurred in that period. Okay. I want to bring a couple more things to your attention. Okay, I know we're... So the greenhouse effect, what is the greenhouse effect again? Okay, we'll briefly review it. Okay, the light coming from the sun is visible light. And what we emit is infrared light. Okay? And if you don't want the earth to warm up, the energy coming in should be emitted out. Okay? Now, your atmosphere has different properties to visible light and infrared light based on its composition. Okay? So if you put the greenhouse gases, what the greenhouse gases do is the greenhouse gases don't care about visible light. They'll still let in visible light. What they do is they'll absorb the infrared light and emit it in all directions. So the infrared radiation gets trapped. More greenhouse gases there are in the atmosphere, more of the energy gets trapped. And less is radiated, and so the earth warms up. Okay, so you know all this. Okay, so so carbon dioxide, see the concentration is the greatest. Today it's 420 parts per million. Okay, CFCs are 530 parts per million. Okay, so CFCs, you see they are 10,000 times as potent as carbon dioxide in trapping infrared radiation. Okay, so they're bad. Most of the damage again is being caused by carbon dioxide. Okay, radiative forcing. So you see the CFCs are trapping about 10% of the heat that carbon dioxide is trapping. Okay, so that's the table. Again, this is an old table, but this is from your textbook. Okay, so I just wanted to bring your attention to that. Okay, so this is concentrations in 2012. Again, that's the problem with textbooks in this field. 10 years is ancient history. Okay, so the greatest environmental challenge facing mankind is global warming. CFCs are chlorofluorocarbons, compounds containing chlorine, fluorine, and carbon. Okay, so here's one example. This is okay, and freon is the most common. Okay, so these are man-made gases. In freon in the past 50 years, CFC emission has increased considerably. So we've started using freon and stuff like that, and that inevitably leaks into the atmosphere and so on. Okay, and again, CFCs are, like I said, 10,000 times more potent. They're colorless, odorless, chemically non-reactive gases. So they're stable. They'll last a long time in the atmosphere. Once you go to your cars and release all the freon into the atmosphere, and it'll be there for another 100 years. You know. Okay. So, okay, again, just want to point that out. Okay, and they're trapping as so. Their parts per trillion. That's 1,000,000 times less concentrated, but see their effect is quite large. Okay. All right, of course you've seen CO2 levels go up tremendously and the earth is warming. So here's for the past 800,000 years, 1,000,000 years. So this is showing you CO2 concentration and the temperature. So CO2 warms the planet. Okay. Now, if no action is taken towards CO2 emission, okay, temperature by 2100, this is the best case scenario, 1.4 degrees Celsius. Now that's too conservative. Temperatures could rise by as much as 6 degrees Celsius. Bad news. Okay? So you guys have to get in office and do something about this. Okay? So this is so global cumulative mass change in glaciers. Okay, so this is just in the past 70 years. What this is showing you is, okay, I'll tell you. So mass meters water equivalent. Okay, what this means? Yeah, that's slightly technical. Don't worry about it. What this means is Okay, so take every glacier, go look at every glacier, and in the past 70 years, the top 25 meters has melted. What is 25 meters? 25 meters is the height of that 5-story building. You see the healthcare building across the science building? So the height of all the glaciers has decreased by that. Global sea levels, this is in millimeters, from 1900, in the last 150 years, has risen by 300 millimeters, a foot. Okay. So an increase in sea levels is a result of two factors, the melting of Antarctic ice and increase in volume of seawater resulting from the increase of average sea temperature. Biological changes include dates of annual migration and certain stages of plant development and all. And the permafrost is thawing. Okay. That has a lot of methane in it, okay, trapped in it, and El Nino and stuff like that. Okay, so here's global warming evidence, and here are the skeptics. Anyway, if you like that stuff. All right.